In this set of notes, we're going to start to introduce the idea of simple linear regression. Often we would like to use sample data to investigate the relationships among groups of variables and ultimately create a model for some variables that can be used to predict its value in the future. The process of finding this model is a statistical technique known as regression analysis, and that's going to be the whole purpose of this course. And so what we're going to do is we're going to start with the most simple form of regression analysis, which is called simple linear regression, and then we're going to build on that and learn how to incorporate multiple variables and do many other things. In order to do this, though, we're going to start out by just giving an introduction and some motivation to the idea of regression. So for example, suppose a researcher wants to predict an infant's birth weight for infants born at hospitals in Lexington, Kentucky in the last year. The researcher could select a random sample of infant records from the thousands born in the past year. The researcher could then use the average or mean of the random sample of infant weights to estimate the infant's birth weight for the infants born at the hospitals in Lexington, Kentucky in the last year. So notice here, what we're talking about is something very similar to what you heard about in your introductory statistics class. Notice here we're going to use the average or mean of the random sample, so that would be the x bar, to estimate the infant's weight for, and that should say all infants born at the hospitals in Lexington, Kentucky, so in other words mu. So we're still working on this idea of using statistics to estimate parameters. In regression, the variable to be modeled is called the dependent or the response variable, and its true mean or its expected value is denoted by either of these two notations. Your textbooks use the mu sub y, so what this is saying here is the function, the mean is, it is the mean of all y's, or a parameter. Many other textbooks will use this expected value of y notation, but they mean the same thing. So for this example, y is the infant's birth weight for infants born at hospitals in Lexington, Kentucky in the last year, and mu y is the mean infant birth weight for infants born at hospitals in Lexington, Kentucky in the last year. So again, notice that this is a parameter. The dependent or the response variable, we denote that by y. And that is going to be the variable that we want to model or that we want to predict. To our first example, where we wanted to model birth weight. So suppose the researcher knows that the actual birth weight for an infant will depend on other variables, such as maternal age of the mother, length of gestation, and a mother's blood pressure. And in general, when we talk about the relationship of variables, usually what we're going to try to do is to model one variable based on the values of another variable. So in this case, we can say that the true weight for a given infant birth is equal to the mean birth weight for all infants plus some random amount which is unknown to the researcher. So here, what we're looking at is the y is going to represent a birth weight. This is the mean of all birth weights. And we know that each time a baby is weighed, what we could do is we could compare that weight to the mean of all birth weights, and each individual is either going to fall some below or some above the mean. And so that difference for each individual's weight compared to the mean, we can consider that difference to be some random amount. And so this random amount we denote with the epsilon. And so the mean of all birth weights, that is this fixed amount plus this random component. So therefore birth weight will also be random, because what the actual birth weight is going to depend on what that random amount is. One strategy, since the random amount is unknown, is to predict the weight of a given infant using the mean weight for all infants, that mu y. And so this will lead us to what we call a probabilistic model for y. For example, if we know that birth weights, or y, are normally distributed with a mean of 3,000 grams and a standard deviation of 700 grams, then the probability birth weight will fall within 2 standard deviations of the mean is 95%. And this comes from what is known as the Empirical Rule. And in order for this rule to hold, we need that normally distributed assumption. And so that's a property of normal distributions that we anticipate 95% of the observations to be within 2 standard deviations of the mean. So what we're going to do is we're going to use sample data to estimate the mu y and the random error epsilon. However, what we're going to find out later on is that a standard assumption in regression analysis is that the mean of the random error is 0. And so based on that assumption, we only need to estimate mu y. And so the question here, what is the difference between what we call a deterministic model and a probabilistic model? So let's look at a common deterministic model that you might be familiar with. So one deterministic model could be area equals height times width. If I tell you the height and the width of a rectangle, you automatically know the area. You know, there's not different potential areas for different heights and widths. So this is what we call a deterministic model. Notice that all of the components here are fixed. Nothing here is random. Whereas in a probabilistic model, we're going to have a random component. And so the probabilistic model we are going to work with is y is equal to mu sub y plus epsilon, where epsilon here is the random component, and that's what makes this a probabilistic model. And so here, looking a little bit closer at that probabilistic model, notice one thing that we could do is here, instead of just having mu y, I have mu y given x. So let's talk about what that could mean. So y is still going to be the value that we are interested in. So this could be birth weight from our previous example, or whatever variable it is we want to model. Epsilon is still going to be that random component, and so that's going to be that deviation from the true overall mean. And then now, instead of just having sub y, we have sub y given x. So this is still going to be the true mean of what we're interested in. But what we can do is, by conditioning on that x, we can make this a function of other variables. So by writing it this way, if we think back to our birth weight example, we're no longer going to model a new birth weight just off of the average of all birth weights. This is how we can start incorporating other variables like maternal age, length of gestation, things like that. And we're going to talk about why this is important. So the simplest method to estimate mu y would just be use the sample mean y bar. So the simplest way would just to say, I'm going to predict my variable based off of the sample mean of that variable. And so if we do that, notice this is our new prediction model. Anytime you place a hat over top of a variable, this means that it is predicted and no longer random. So here what we're saying, in terms of our birth weight example, we would be saying, I'm going to predict that all new birth weights are equal to the average of my sample of birth weights. And so the question here, is that going to do a very good job? And the answer is no. Really what we need to do is we need to incorporate other variables. If I want to predict an infant's birth weight, I know that I shouldn't just use the sample average of birth weights from the data I collected. Really what I should do is I should consider that infant's individual circumstances. I need to incorporate things like maternal age of the mother, length of gestation, mother's blood pressure, etc. And so these variables that we're going to incorporate to help us predict what's going to happen, we call these the independent or explanatory or predictor variables. You know, all of those would fit into there, and they all mean the same thing. These are generally going to be denoted by x1 through xk. So typically in a regression model, our response variable we use y, and our explanatory variables we use x. And the process of finding a mathematical model that relates y to a set of independent variables and best fits the data is part of the process known as regression analysis. And regression analysis uses a mathematical model to predict a variable y, that should say from values, not from values of the other variables x1 through xk. And so this is kind of the idea behind regression analysis, what it is we're trying to do. So next what we're going to do is look at what is called the straight line probabilistic model, or simple linear regression. This is the most basic form of linear regression. The simplest model for relating a response variable y to a single independent variable x is a straight line. So in this note set, we're going to discuss simple linear models, and we'll show how to fit them using the method of what is called least squares. So we're going to start out by just defining our model. So recall that any straight line that you draw can be defined by the y-intercept and the slope. So our straight line model that we're going to build is going to be a straight line, and it's going to need a y-intercept and a slope. So here we have our definition of our first order straight line model. And so these two pieces right here, these are actually what are going to help us model that mu y that we saw later on. And we're modeling it using a straight line. And so here we have the y-intercept, and here we have the slope. So beta naught and beta 1 are both parameters. So just like you saw in your introductory statistics course, since these are parameters, we're going to use sample information to estimate them, and we'll see how to do that here in just a little bit. And then finally the epsilon, remember that is the random component. And then y, that is the dependent variable. Okay, and then I have all of those defined down here at the bottom. So let's kind of look at a picture of what this straight line model looks like. So here we have our straight line model, and so there are multiple ways that we can actually denote this. So the one way that we just saw was that y was equal to beta naught plus beta 1 x plus epsilon. We could also denote this in terms of our expected value. So remember up above I said that beta naught plus beta 1 x, that was equal to the deterministic component, or the expected value. So you could also specify the model this way. Or instead of mu sub y, we could have the expected value of y. All four of these are all three of these are ways to specify the model. So since this model is a straight line, here on this plot we've got this dark straight line here to specify it. Looking at our two different parameters, the beta naught is our y-intercept. It's where our line crosses the y-intercept. And then the slope, what the slope tells us is for every 1 unit increase in x, it's telling us how much y increases. So if we go over x 1 unit, beta 1 is how much y is increasing. Now, in order to fit any kind of regression model, there are always going to be model assumptions. And we're going to spend a lot of time later on in the notes, later on in the semester, really diving into what are the assumptions for regression and how do we check those assumptions. We're going to spend just a little bit of time here with simple linear regression, but we're going to spend a lot more time on it later on when we learn about more complicated models. And checking the assumption, understanding the assumptions is a very important step because it really talks about the validity of your model and whether or not it's valid to fit that model to your data and to use it to get inference. And it's one of those things that I think often gets overlooked by people, because when we read methods sections or we read results, nobody really talks about the checking of the assumptions. It's something that's kind of done in the background, but it's very important. So for the least squares regression model, there are 4 basic assumptions that we make about the general form of the probability distribution of epsilon. And so what you're going to find out is, as we move forward, most of the assumptions we make about the model are going to be about that random piece, or the epsilon. So again, we have this probabilistic model, and these are 4 assumptions that are generally made. One is that the probability distribution of the mean of the probability distribution of epsilon is 0. That is, the average of all of the errors over an infinitely long series of experiments is equal to 0. The variance of the probability distribution of epsilon is constant for the same settings of the independent variable of x. So in other words, for different levels of our independent variables, we should see similar variability in our y. The probability distribution of epsilon is normal, and the errors associated with any 2 different observations are independent. And so all 4 of these are generally summarized with this notation right here. It's kind of a shorthand way to summarize it. Or, as you can see here on the next page, we could also summarize them using LINE, linear, independent, normal, and equal standard deviations. And again, I'm not going to spend too much time here because we're going to come back to this idea later on. Alright, let's look at a new example. This one says a sociologist assigned at a correctional institution was interested in studying the relationship between intelligence and delinquency. A delinquency index ranging from 0 to 50 was formulated to account for both the severity and frequency of crimes committed, while intelligence was measured by IQ. The following table displays the delinquency index of a sample of 18 convicted minors. So we do have a sample data set here. Here our independent variable is going to be IQ, and our dependent is going to be Y, or we could say our predictor is IQ, and our response is Y. Again, different names for the same thing. And so what we're going to do is we're going to define the straight line model. Again, so here's our model that we've seen before. And we're going to use the data to estimate the unknown values of beta naught and beta 1. So again, these are parameters. And what we're going to do is we're going to use sample data to estimate. And what you're going to find out is when we use the sample data to estimate what these values are, we're going to call the estimates beta hat naught and beta hat 1. So these are both going to be statistics. So here's a scatter plot of delinquency index as a function of IQ. And as we can see, this is reasonably linear. So remember, when we say that a plot looks linear, we don't necessarily mean that all of the points fall on this really nice straight line. What we can see here is if we drew kind of a thick straight line, they would fall reasonably there. Now we do have one outlier, and later on in the course we'll talk more about what to do with outliers and also what we could call an influential point, and what we need to do when we consider those in our analysis. So down here at the bottom, we've got several definitions that relate back to the scatter plot as well as our linear regression model. So the scatter plot, that is the graph that you see up above. The errors in prediction. What the errors in prediction are is these are the difference between the observed y values that we see and then the y values that are predicted based off of our model that we fit. So let's go up here and look at our scatter plot and see what that would look like. So right here, the line that is on this scatter plot, this line is not our model. This line is what we call our fitted line. And so we denote our fitted line by y hat is equal to beta hat naught plus beta hat 1 x. So in this case, the x's are our IQs, and the y hats, those are the y values that fall along this fitted line to predict what delinquency index is for different values of IQ. And then the beta hat naught and the beta hat 1, those are the actual slope and intercept of this line. So, for example, if we look at, let's look right here at an IQ of 120. So notice here I'm looking at this point, and this point has an IQ of approximately 120, and it had an observed delinquency index of approximately 11. Now what I could do is I could see what y is predicted with an IQ of 120. And our fitted line suggests that if a minor has an IQ of 120, if we go across here, let's say a delinquency index of approximately 23. So this point where we intersect the line is 120 and 23 approximately. So here, the 11 is a y because we observed it, so it's a y, but the 23, that is a y hat because that is the y that was predicted for an IQ of 120. This vertical distance between the two, or this discrepancy between what we observed at 120 and what our line predicts at 120, this is what is known as the residual. And we can see that down here, oops, in our definitions. For each of our 18 observed points, we can calculate a residual. In other words, for each of the 18 points that we observed, we could see what is the discrepancy between what we actually observed in our data set and then what our fitted line is predicting. And we call these the errors in the prediction or the residuals. And the whole idea of a linear regression line is to find the line that minimizes those distances. Now, the problem is notice that some of the observed points are going to be below the fitted line and some of them are above. And it ends up that the way that linear regression is done, if you add those up, they're going to cancel each other out and they're going to be equal to 0. So for that reason, we want to work with positive values. So what we do is we actually work with these squared errors. And so one way to visualize this is what we're doing is for each of the observed points compared to the line, we're drawing a square. And so the area of this square for each of these points, and we do this for all 18 of them, those represent the squared errors. And so the idea is we're trying to find a line that makes those squared errors as small as possible, and that's what linear regression does. And you can read a little bit more information about that here in these definitions. So let's talk about how we actually get those parameter estimates. How do we actually find beta hat naught and beta hat 1? And so again, we start out here with a definition of the residual, and that's what we just saw up above on the scatter plot. And again, the idea is if we looked at all of these squared residuals, we want to minimize that. And the quantities that define that line, the beta hat naught and the beta hat 1, that make that a minimum, that's what we call the least squares equation. And so here is our definition of our least squared equations. It is the one where all the sums of the residuals is 0, and the sum of the squared errors is smaller than for any other straight line model. And so here is the formula. Now we're not going to do a whole lot of calculations by hand in this class, but I would like to do one set of these for the simple linear regression just so you can see what is involved here. And the majority of the time, again, we're going to use software to actually find these estimates. So in order to calculate these by hand, what we're going to do is we're going to set up a table from our data to help us out. And so we're going to continue this idea of the IQ and delinquency index example. So what we've got here in our first two columns, this is our data set. And so here we have our IQs, so there's 18 different IQs here, and then we have our 18 different delinquency index that match with those IQs. So that is our sample data set. Now, in order to calculate these estimates, we need to do some stuff with our data, and the easiest way to do this is to set this up in a table, and I've already done that for you here. So notice the next column that we have right here, this is going to be all of the x's squared. The fourth column is all of the x values times the y value, and then the last one is the y value squared. Down at the bottom of the table, we've totaled each of those columns, and then we also have the mean of x and the mean of y. And we're going to use all of these values to help us get those estimates, and we do that by looking at different sums of squares. So the first two pieces of information we need to get is the sum squares of the xx and sum square of the xy, and we have those different formulas listed here, and so we can just fill in those values. So looking here at our first formula, notice the first term we need is the sum of the xi squared, and that's given to us right here. N is going to be our sample size, and we have a sample size of 18 in this case, multiplied by the mean of the x's squared. And then if we put that in our calculator, now I am going to round this to 4 decimal places, so for that reason we might get a little bit of round off error, and so keep that in mind when we look at the software output later on. We're going to do the same thing for the sum square xy, and again here's our formula. So the first thing we need is the sum of the x values times the y values. Notice that's given to us right here. We're going to subtract off n, which again that's our sample size of 18, multiplied by the mean of the x values times the mean of the y values. And so now both of these values are going to help us actually find our estimates of the y-intercept and the slope. So the first one we're going to find is the estimate of the slope. So the first thing we're going to do is use those two values that we just found up above. Alright, so a couple things to notice here. First thing to notice is this term is denoted by beta hat 1. The reason it has the hat on it is this value is found using sample data, so it is a statistic. The other thing to notice is that the value we found is negative, so in other words this suggests that the slope is negative. So it's always a good idea to go back to your scatter plot and say, does that make sense? Should our slope be negative? So let's go back up to our scatter plot. So here is our scatter plot, and we can see based off this scatter plot we should find a negative slope. So that is reasonable. Alright, next we can find the slope that we just found to find our y-intercept. And again, notice this is a statistic. We did calculate this from sample data. And so from here we get the least squares regression line. So notice this is not the model, this is the fitted line. So for this reason we don't use y, we use y hat, and then we substitute in the values of the statistic that we just found. And now each of these statistics has a particular interpretation, so let's write down what those interpretations are. First thing we're going to do is we're going to interpret the estimate of the slope. So the estimate of the slope is on average. We estimate that the delinquency index will, and here we're going to have decrease, and the reason I'm going to have decrease is because my slope was negative by 0.2489 points for every additional IQ point. Okay. So that's my interpretation of my slope. And now we can write down the interpretation of the intercept. So for our intercept, we estimate that the average delinquency index for we estimate that the average delinquency index when IQ is equal to 0 is 52.2732. Because remember that this is the y-intercept and that occurs when x is equal to 0, and our x variable in this case is IQ. So the question is this interpretation meaningful? And the answer here is no, and it's no for two different reasons. The first one is that we do not have data for IQ equal to 0, and it does not make sense to discuss an IQ of 0. So what you're going to find is talking about the interpretation of the slope is always appropriate, whereas the intercept may or may not be appropriate. In order for the interpretation of the intercept to be appropriate, you need two things to happen. The first is it needs to be reasonable to talk about your x variable being equal to 0. The second is that if it is appropriate, you need to have data in that region as well. And so we talk about that a little bit here. In order to have that interpretation make sense, again, one of the conditions is we have to have data around x being equal to 0. If you don't have data in that region, then that is called extrapolation, and we cannot use, or we cannot have extrapolation when talking about the interpretation or making predictions with our model. And then so finally the last thing here is I just want to show you using software where you can find the intercept and the slope values. And what you're going to find as we go throughout the notes, you're going to see these two different pieces of computer output quite a few times. So don't worry if you're not sure of what all of the output is right now. We're just going to focus on two small pieces. First one, looking at our output. If you want to find your slope and your intercept, they're always going to be found right here. The intercept will be labeled intercept, and then the slope is always going to have the label whatever you called your x variable in your data set. So for this particular data set, the name of the data set was this, and then the variable was IQ. And you'll notice here for our intercept and our slope, you know, up to rounding difference, these are the exact values that we just got when we did this example by hand. And then next we have the same problem but in SAS output, and you'll see very similar output. Here's where you find your intercept and your slope, and again these values are very close to what we found when we solved this problem by hand. Alright, so the last thing we're going to talk about is residual analysis for the simple linear regression, and I'm just going to briefly talk about this idea. And the reason for it is we use a residual analysis to determine whether or not our model assumptions have been violated. Later, after we've talked about multiple regression, we're going to spend a lot of time talking about how to perform a true residual analysis. So here I just want to briefly mention some things that are done, but I don't want to spend a whole lot of time on it at this point because again, we're going to spend a lot of time on it later on. So if we want to check the assumptions stated regarding that error term, what we do is we're going to look at the residuals. And so remember there are 4 assumptions. We have that those errors are normally distributed, they have a mean of 0, the variance is constant for different values of x, and all the pairs of errors are uncorrelated or they're independent. We can check them using the model residuals. And so just to recall what the residuals are, the residual is the difference between our observed y and our predicted y. So we calculate our residuals by looking at each of our observed values of y. So thinking in terms of our example we've been using throughout these notes with the IQ and the delinquency index, we had 18 observations, so we can calculate 18 different residuals. And so how we do that is, notice if we look at our observed y's, which are our observed delinquency indexes, we could use our model to predict what the delinquency index would be for different levels of IQ, and we get the predicted values. So each of the residuals is going to be the difference between the observed and the predicted. So in this case, if you took the 26.2, you subtracted off the 24.8906, you would get that residual. And what we do to check our assumptions is we're actually going to look at plots of these residuals. Now by default, R gives a really nice what we call fit diagnostics for the model. So we're going to look at SAS output here. In lab, I'll show you how to make these in R. So SAS gives a lot of different fit diagnostics. For right now, we are only going to focus on these three. And again, later on when we give a much more detailed treatment of the residual analysis, we'll look at some of these other plots. So here we have a list of some plots to look at, and so we'll go back up to the top and look at each of these. The first one is to plot the residuals on the vertical axis against the predictor variables on the horizontal, and we'll call this plot 1. This type of plot helps to see if the distribution of the residuals is uniform around 0, and that would suggest constant variance. It's also used to check if the linear model assumption is appropriate, and so the point should look like random scatter. So looking up at the top, that's this plot right here. And so when we're looking for patterns, we might look for dips or horseshoe shapes. We also want to see things randomly scattered about 0. So in other words, we wouldn't want to see a bunch of points tightly clustered here, for example, and then spread out further. Now, in this case, we only have 18 observations, so we do have to keep that in mind. I do notice looking here, it looks like there is a point that's kind of out here by itself, so that point concerns me just a little bit, but this doesn't look terrible considering that we have that small sample size. The next two plots is we can look at histograms, and probability or quantile plots are used to assess the normality of the residuals. So these are going to be plots 2 and 3. So here is your quantile plot, and here is your histogram. So looking at both of these, I don't see any large deviations from normality. Our QQ plot, we generally want it to be fairly linear. It does look fairly linear. Again, we do have that one point that I'm a little bit concerned about that I probably want to comment on. But again, only have 18 data points. And looking at my histogram here, it is roughly symmetric. It does have a slight skew. It's not perfect, but what you'll find out when you work with real data, especially with small sample sizes, you're not likely to get perfect histograms or perfect QQ plots. So we're looking for large deviations that really make us question that normality, especially when we've got small sample sizes. And then the last thing we could look at is if we have time series data, then we could look at a plot of the residuals to see if we see any patterns through time. If we do not have time series, then it doesn't make sense to look at this. So in this particular case, we've got these observations from 18 different minors. None of this has been taken, we're not looking at the same individual through time. This is not time series data, so we're not going to worry about that for this particular data set. And then finally, there's a small comment here about how we can use standardized residuals to look to see if a point is an outlier or not, and we can talk about what we need to do with those. But again, for right now, this is all I really want to say about the assumptions, is just, just this little piece, because again, we're going to spend a lot of time on this topic later on. And this is going to conclude this note set.